All right, let's take a look at the Unit 2 review on thermodynamics. The first one says Tasman Lake in New Zealand is a lake formed from the retreat of the Tasman Glacier. It has a surface area of 6.91 kilometers squared. Assuming the surface area remains constant, if a glacier with the following dimensions completely melts into Tasman Lake, how much will the level rise in meters? Hint, 1 kilometer is 1,000 meters. Please round your answer to the correct number of significant digits. All right, so first thing we're going to need to do is find the volume of the glacier. So we've got 307 kilometers times 0.020 times 0.0054. So the volume of the glacier is, oops, I want to do that, 0.0332 kilometers cubed. And then we know volume divided by area is equal to the height of sea level rise. So we're going to do 0.0332 divided by the surface area, 6.91. That's 0.0048 kilometers. And then we know that 1 kilometer is 1,000 meters. I'm going to show my work here with dimensional analysis. Oops, draw red. So 0.00, ooh, this is 2 significant digits. So my final answer should end up being 2 significant digits. Okay, this is good. 0.0048 kilometers. I know that 1 kilometer is equal to 1,000 meters. Multiply across the top, divide by the bottom. It comes out to be 4.8 meters. All right, record the following measurements to the correct number of significant digits. Let's zoom in. So this is 70, 71, 72. It looks like it's exactly 73, but because it measures to the ones place, we need to estimate out one more. So we would say 73.0 milliliters. And then we've got a ruler and it goes by the point ones place, 2.1, 2.2, 2.3, 2.4. So because it goes to the tenths place, we need to estimate out one more. So maybe 2.35 centimeters. If you measure exactly 30 milliliters of water using a pipette that has increments to the hundredths place, how should you record it? Well, it measures to the hundredths, so you need to estimate out one more to the thousandths place. So you would record 30.000. All right, let's apply rules about significant digits. Let's see. You have a piece of metal that has a volume of 15, a mass of 135. What's the density? Density is mass divided by volume. So 135 divided by 15, that's grams per milliliter. This number has 3 significant digits. This one only has 2. So our answer should just have 2. So rather than write 9, we would write 9.0 grams per milliliter to make sure we have 2 significant digits. Okay, showing our work with dimensional analysis, let's convert 132 millimeters into feet. So we've got 10 millimeters equal to 1 centimeter. And we know 2.54 centimeters is equal to 1 inch. And we know 12 inches is equal to 1 foot. So millimeters cancels, centimeters cancels, inches cancels. We want to multiply everything on the top, so 132 times 1 times 1 times 1. And then everything on the bottom, 10 times 2.54 times 12. So then we've got 132 divided by 304.8. And our answer should have 3 significant digits. You might say, hey, wait a second, this only has 2. But when you have an exact conversion like this, it's really like saying 1 centimeter is equal to 10.00000 forever. So you still go by the measurement. So our final answer here would be 0.433 feet, because that's 3 significant digits. Using Microsoft Excel, the following graph was made from the mass and volume data. What is the density of water? Well, since this is mass per volume, change in y over change in x, the slope, 1.09, is equal to the density of the water. So that's it. Describe what happens at the particle level from the before picture to the picture on the right. Okay, I'm going to type this out. The red particles have a higher temperature and therefore more kinetic energy. So they are moving faster, vibrating faster, since this is a solid, and they collide with the cooler white particles that are moving slower. The red particles speed up the white particles, and in the meantime, they slow down themselves. The final temperature of all the particles is the same, thermal equilibrium, and somewhere, well, in this case, the two blocks are the exact size, and because the masses of the original blocks are identical, the final temperature will be exactly the average of the two initial temperatures. Okay, it looks like something got moved on my, let's move this down. Okay, use the image below. Object A is big and has an initial temperature of 120. Object B is small and it has an initial temperature of 0. When they are in contact, what will the final temperature be? Okay, so object A weighs 50 and object B only weighs 10. That's a ratio of 5 to 1. That means the temperature change ratio of A to B will be 1 to 5. It's the inverse. So the total difference in temperature is 120. Okay, and then we're going to add 1 plus 5, 6. And we're going to take the total temperature divided by that 6, that's 20. So the ratio of the change in temperature will be 20 to 100. That's 1 to 5, and it adds to 120. Another way of doing this, if you're uncomfortable with that, is you can say, okay, 1x plus 5x equals, in this case, 120. So that's 6x equals 120. Divide by 6, divide by 6, x equals 20. And then if you go and plug it in, 1x is 20, and 5 times 20 is 100. So the change in object A's temperature will be 20, and the change in object B's temperature will be 100. So the final temperature when they reach thermal equilibrium will be 100 degrees Celsius, which makes sense because this is so much bigger. So the final temperature is going to be closer to the bigger one. So the change in temperature is 100, and the change in temperature is 20. Okay, equal masses of water and iron are both heated with 100 calories of heat energy which one has the greatest temperature change, the water or the iron? So the specific heat of the iron is a lot lower. So that means it will have the greatest temperature change. The iron will have the greatest temperature change because it has a lower specific heat, which means it takes less energy to change an equal amount of it as water by 1 degree Celsius. In other words, iron is much easier to heat up than water. Using the equation below, how much heat in calories transferred to 106 grams of water? How much heat in calories transferred to 106 grams of water if the temperature went from 22.5 up to 89.9? Okay, so we want to solve for Q. The mass of our water is 106.5. The specific heat of water is always the same, 1 calorie per gram degrees Celsius. And our change in temperature, 89.9 minus 22.5, oops, that's 67.4. If I notice what happens with my units, everything cancels out except for calories. So now I want to do 106.5 times 1 times 67.4. I want to pay attention to my significant digits. There's 3 here. So that means the answer is 7,180 calories. Oh, there we go. How much energy in calories would it take to melt a glacier that has a mass of 5.8 times 10 to the 17th? Well, it says here it takes 80 calories per gram to melt ice. And here we're trying to melt 5.8 times 10 to the 17th grams. So we need to multiply. So 80 times 5.8 E17, 4.6 times 10 to the 19th grams. Again, because it's 80 calories to melt 1 gram, we're trying to melt 5.8 times 10 to the 17th grams. So we want to multiply those together to get our final answer. There we go.